Hi, Patrick. Thank you so much for offering me the opportunity to submit this as late as it is. I really do appreciate this. So obviously I'm going to be doing my Module 3 presentation. Today I'm going to be talking about the general linear model, and within that, multiple regression correlation and analysis of variance as well. So the general linear model is like the multiple regression model in that we are attempting to characterize the relationship between a given number of predictor variables and an outcome variable. But it differs from multiple regression because it gives us a little bit more flexibility. So we can look at, for example, more than one dependent variable. And we can more appropriately analyze repeated measures designs. And then we can account for both continuous and categorical variables. It is a linear model, meaning it is additive. And the two types of analyses that fall within this general linear model are multiple regression correlation and analysis of variance. So the primary difference between these two being that we typically use MRC for continuous variables and ANOVA for dichotomous variables. However, according to the King reading, when we're talking about dichotomous variables in specific, ANOVA and regression are for all intents and purposes the same because they have the same underlying assumptions. So as long as you have dichotomous independent variables, you could use either type of analysis. But generally speaking, the purpose of MRC is to examine the relationship between several continuous predictor variables and outcome variables. And so we're asking how much variance does each of these variables account for within our model. And also we can use this tool for inferring or forming predictions about future occurrences. So we estimate parameters through the least squares principle, where our aim is to minimize the sums of squares for our predicted errors or residuals. And this regression equation that I have on screen gives us our best guess prediction of y when we have a given x value. And so error or residual is found by subtracting the expected value minus the observed value. So I can just run through my hand correlations here. I have the multiple regression correlation hand calculations on the left, and then ANOVA on the right. So now moving into MRC, looking at the following output for my multiple regression correlation, we see that there are three predictor variables, x1, x2, and x3, and the one outcome variable, y1. The first thing we can note using the p-values is that at the 0.05 level, none of these main effects are significant. So this means that none of the three independent variables on their own are good predictors of our outcome variable. Therefore, we fail to reject the null in this case. So now we can kind of talk about our assumptions for multiple regression correlation. So one of them is that there should be no perfect multi-collinearity between our predictor variables. So no two predictors are perfectly correlated with one another. And the reason being, if we have a high degree of collinearity, we'll also have higher standard errors. So this means that we can't be as confident in our estimates or in the predictive power of our model. Also, we have less chance of rejecting the null hypothesis, so an increased chance of type 2 error. So if I look at, in my output, if I look at the tolerance and VIF values, I can see that for variable x2, the tolerance value is quite high, and our VIF value is fairly close to 1, so maybe not as much cause for concern there. But for variable x1 and x3, the tolerance values start decreasing, and our VIF start moving closer to 2. And not that these are particular benchmark values or cutoffs, but we might want to assess for the possibility of multi-collinearity, especially given that we failed to reject the null earlier. So other assumptions that I'm going to talk about are mostly related to our residuals or our error. They're important to note because violating any of them could make statistical inference more problematic. So the first one is normality. Looking at my QQ plot, the residuals for my model are fairly normally distributed. So in other words, they follow that diagonal line pretty closely, with the exception of maybe that one point on that far left side. My other assumption is that I have independent residuals. So my second graph shows that the standardized residuals plotted with the standardized predicted values of y1. And what we want ideally here is points that fall equally on both sides of that middle line. And we see that the plots generally mirror this line. So we're okay with regards to our residuals being independent from our IV. And then our other assumption is homoscedasticity. The variance of the error is constant for all values of the independent variable. So with that assumption, I look at my third graph and see that this is generally the case, although there are some irregularities. And then a mean residual of 0, my output did confirm that I do have a mean residual of 0, so this was the case. And finally, with regards to outliers, I can look at Cook's distance to assess whether any outliers might be present in our regression model. There are some rules of thumb that different researchers use to examine Cook's distance values, but in the Fox book, we're kind of warned against relying too heavily on these. And Fox suggests that plotting might be helpful in assessing outliers, so I just kind of went with that route and plotted them. And it seems like there might be one point that might be worth looking into a little bit deeper to see if it is an outlier. Okay, so now I'm going to talk about my ANOVA. So for ANOVA, the purpose is to help us determine whether the variance or uncertainty around means is statistically significant. If we have a great deal of uncertainty around a mean or around each mean, then we can't really judge with any amount of confidence whether those two means differ. And so an example of this that we use quite frequently is t-tests, because this is a simple form of ANOVA. However, with ANOVA, we typically use an F ratio instead of t-scores. So in my ANOVA, I'm looking at two different factors, F1 and F2, with regards to my outcome variable, and I stuck with the same one, Y1. Looking at the output, I can see immediately that as far as the independent effects of F1 and F2 go, we don't really seem to have any significant predictor of Y. In other words, we fail to reject the null hypothesis in this case. Now, Cortina in his 2002 article argues that we can take the embedded null approach and look at a non-significant predictor variable within an interaction to see if there is in fact a significant relationship that we're not catching on to immediately. However, in the case of my data, this doesn't seem to be true either, because the interaction effect is non-significant as well, so it's preventing us from rejecting the null in that instance too. So just like MRC, there are some underlying ANOVA assumptions. One is homogeneity of error variance. So looking at the output for Levine's test on the upper left-hand corner, we see that the variances are not significantly different, so we fail to reject the null in this instance, meaning we can say that there is homogeneity of error variance. And then another assumption is that we have independent error or residuals. So we see in the second graph that the line is at 0, so we do appear to have independent residuals. And then a normal distribution of errors in the QQ plot, we see that the residuals are fairly normally distributed. And then finally, for outliers, again, I have them plotted there, I have the Cook's distance plotted, and so we can see there is a single point that might be worth closer examination. And so that is the end of my Module 3 presentation. Thank you again, and I hope you have a good night, Patrick. Thank you.